So hello and welcome to this lesson in differential equations 2. So in this lesson we learn how to find the solution of differential equations using the series solutions method. Okay, so we'll be considering ordinary differential equations of the second order which are homogeneous. So we are going to solve these two questions here, and after solving those two questions I'm very hopeful that you will get the understanding of the concept. Okay, so let's take the first question. So whenever we are finding the solution of a differential equation using the series method, the first thing that we do is that we assume that y of x equals summation with n starting from 0 to infinity a n x n is a solution to the differential equation. So we always assume this. Okay, so after assuming this, then we can find y prime of x and also find y prime prime of x and make substitution into the question which was given to us. So you could see that we have, so the first thing we do is that we assume that y of x is equal to this. So when we differentiate this, we will get, so when we differentiate xn, we get n, right? Then a n x n minus 1. And actually the reason why when we find the first derivative this here start from 1 is because when we should expand y of x, okay, you see that you get a naught x naught plus a1 x1, right? So you don't write that, then plus a2 s squared. So you see that the first term is a constant a naught, so when we differentiate it, it will go away, so the terms will start from here. So that's the reason why when we find y prime of x, we start from what? 1. The same way when we also differentiate y prime of x, e1 of s goes away, so we start with the index 2. So if we were to find y prime prime of x, that one will start with 3. Okay, so there's our y of x, y prime of x, and y prime prime of x. The next thing that we do is that, the question given was y prime prime plus y equals 0. So we make substitution into this. Whenever you find y prime prime, we put this there, and where you find y, we put this there. So making substitution into the question, we end up with this. Okay, and when we get this, what we do is that the index here, they should be the same before we can add these two sums, and also the exponents here should also be the same before we can add them. So we have to do what we call shifting, so we have to shift them. Okay, so we would want to change this to n and also change this to n. So the only way in which we can do that is to let n be equal to n plus 2 in our first sum. Okay, so in here wherever you find n, we put n plus 2. So doing that means wherever you find n, we are putting n plus 2. So we get summing from n plus 2 equals 2 to infinity n plus 2, n plus 2 minus 1. That is wherever you find n, you put what? N plus 2. So an plus 2, then x, n plus 2 minus 2, plus we maintain this one. So you can see that here we have n plus 2 is equal to 2. So we have n will be equal to 2 minus 2, and n will be 0. That's why you can see 0 here. We have n plus 2 here. Here to be n plus 2 minus 1. which is n plus 1. Then here we have n plus 2 minus 2, which is what, xn. Then we maintain this. So now can you see that this is the same as this, and the exponent here, right, is also the same thing. So that means now we can add these two sums. Okay, so when we add them, we are going to get this here. I hope you understand. Okay, so when we get this, then what we do is that we take whatever is here and we set it to 0. So this is what you can see here. And after that, we make this the subject. Okay, so a subscript n plus 2 the subject. So making that the subject will give us this. So after we have this, then what we have to do is that we have to find various values for a depending on the values for n. So we start with when n is equal to 0. So when n is equal to 0, when we put that here, we'll get minus a naught over 2 times 1, because it will be 0 plus 2 and 0 plus 1. So we get a2 will be equal to minus a naught over 2 times 1. Then when n is equal to 1, so when you put n is equal to 1 here, we get a3 will be equal to negative a1 over 1 plus 2 times 1 plus 1, which will give us negative a subscript 1 over what you can see there. Okay, so when n is equal to 2, so we'll have this here. So you see, we can see we have negative a2 here, right? We have a2 here, and we also know what a2 is. So that means we can make substitution. So when you make substitution, we get a4 to be equal to be negative, and now a2 is what, minus a naught over 2 times 1, then times 1 over 4 times 3. So that will give us what we can see here, a naught over 4 times 3 times 2 times 1. Then when n is equal to 3, so we will have a5 will be equal to minus a3, 5 over 4. But we know what a3 is. You know, a3 is given by this here, right? So we can make substitution. And when we make substitution, we are going to get this. So you can continue for when n is 4, when n is 5, when n is 6, 7. You can do as much as you want. So when you do that, you realize that you are going to get two different sets of values. Okay, so you get some for a naught and some for a1, just as we were doing. So you get a2n will be equal to negative 1 power n over 2n factorial a naught, and you will get a2n plus 1 minus 1 power n 2n plus 1 factorial a1. Okay, all right. So now that we have them, then we can use a principle of superposition to find the general solution. So we will have the general solution y of x will be equal to a naught, then summing from 0 to infinity. Then so we put in our a2n, that's what we are putting here. So that's why you can see this here. Then we have s to the power 2n because of this 2n here. So we have s to the power 2n. And when it comes to a1, we get plus a1. So we are taking this one, alright? Minus n power n 2n plus 1 factorial. Then s 2n plus 1 because of this. So those of you who know the Taylor series for cos x about 0, you will see that this here is the same as the Taylor series for cos x about 0, or the Maclaurin series for cos x. So that means you can replace the whole of this with cos x. The same way the whole of this is also the Taylor series of sin x about 0, or is the Maclaurin series for what? Sine x. And so we also replace the whole of this with sine x. So that means that the general solution for our differential equation using the series solution method is y of x equals a naught cos x plus a1 sine x. So let's just take the second example, which happens to be the Airy's equation. So with that one too, what we do is that we always assume that y of x equals this is a solution, right? Then we find our y prime of x, y prime prime of x. Then after that we make substitution. So I realize that part is very simple. Okay, so you should get that. So making substitution into this, right? Because this is our question. So we will get what you can see here, where the whole of this is y prime prime. You see we have our x here, and this is what y equals 0. So when we have this, then you can see that we have x here. So we can multiply this x by this x. So this is the same as x power 1 times xn, which will give us s power n plus 1. So that is what you can see here. I hope you understand. So now we want to add these two sums or subtract them anyhow you want to do it. But before we can do that, we have to make sure that both the index and the exponents are equal. So that means what is here should also be equal to what is here, and this should also be equal to this. So what we can do is that we can first change this to this form. So what we do is that when we take this first part, we let n be equal to be n plus 3. And the reason we are letting n to be n plus 3 is that if this n here is n plus 3, then what we have here will also be Sn plus 1, because we want to make it of this form. So that's how we select let n be n plus 3 or let n be this or that. Okay, right. So that means wherever we find n here, we put n plus 3. So we will get summing from n plus 3 equals 2 to infinity, n plus 3, n plus 3 minus 1. So yeah, you can see this line. So now when we make our evaluation, so you see here for instance, you have n plus 3 equals 2. So you get n will be equal to 2 minus 3 minus 1. So that's why you have minus 1 here. Then n plus 3, n plus 2, en plus 3, xn plus 1. So you can see now this and this are the same, right? But when we come here, here it is starting from minus 1, here it is starting from 0. We have to make sure that that is also what? The same. What we can do is that we can take this one and expand it. You know, it is in the compact form, so we can expand it. So when we expand it, when n is equal to negative 1, we will get, I mean, wherever you find n, we put negative 1. So negative 1 plus 3 times negative 1 plus 2, then a minus 1 plus 3, x power minus 1 plus 1, plus, then we start from what? 0 now, because we've taken it when it is at what? Negative 1. So then we have plus this minus that. I hope you understand. So when we take this part, minus 1 plus 3 will give us 2. So you get 2 minus 1 plus 2 is 1. Then this one will give us a subscript 2. Then you get s power 0, which is 1. So that means we get 2a2 plus. Then now, since we have the same index and the same power, we can add them, right? So plus summation with n starting from 0 to n. So n plus 3, n plus 2, an plus 3 minus an, then xn plus 1. So when you get here, what we do is that what this means is that 2a2 is equal to 0, and also whatever we have in here is equal to 0. So we will have 2a2 to be 0, which implies that a2 is what? 0. I hope you understand. Then whatever is in here is also equal to 0. So making that you can find here. Making an plus 3 the subject, we get a subscript n plus 3 will equal to n plus 3 n plus 2. I hope you get that. Then we start when n is 0, when n is this, when n is that. Okay, because n starts from 0. So when n is 0, when you put it in here, we get a3 will be equal to, so when you put n is equal to 0 here, we get a3 will be equal to a0 over 3 times 2. When n is equal to 1, we get a4 will be equal to a1 over 4 times 3. When n is equal to 2, you get a5 will be equal to a2 over 5 times 4. But you see, we had a2 to be 0 here. You remember? So that means we get 0 over 5 times 4, which is 0. So we continue with it. When n is 3, we will get a6 will be equal to a3 over 6 times 5. But e3 is this here. So we can further make another substitution, and that will give us a0 over 6 times 5 times 3 times 2. Then when n is 5, you get a7 will be equal to a4 over 7 times 6. But a4, we found a4 here. So this is a4. So we can make substitution and we get a1 over 7 times 6 times 4 times 3. So we can continue this when n is 5, 6, 7, 8, 9. So when we would want to stop, okay. The most important thing is that when you are doing that, there is always a pattern. That's when n is 0, when n is 1. So you have to look out for the pattern, okay. If you get it, then you stop it. If you don't get it, continue doing it until you get it. And if you do it well, eventually you realize that it will follow some pattern, okay. So there's a pattern it will follow. You realize that when n is equal to 0, 3, 6, 9, we will always have something of this form. Then when n is equal to 1, 4, 7, 10, 13 going, you would always have something of this form. And when n is 2, 5, 8 and the rest, you always have 0. Okay, so by the principle of superposition, when we look at what we had here, okay, so that means what we had here, here, and for the last condition, that means that we will have the general solution to be y of x will be equal to a naught plus s cubed over 6 plus s6 over 180, then plus a1 multiplying x plus x4 over 12 plus x7 over 4 going. Okay, so this happens to be the general solution. So when you are, so a summary of what you've done, okay, when you are using a series solution method to find the solution of a homogeneous second order differential equation, the first thing that you do is that you assume y of x equals this is a solution. Then based on the question, you find y prime of x and y prime prime of x. After doing that, you make substitution into the question. Then the resulting equation that you get, before you add them, you have to make sure that the index, like what you have here, in all of them should be the same. And also the exponent here should also be the same. So if you have them to be the same, then you add them. If not, you have to be doing some shifts, okay. So after getting them, then you will have some an plus something equals something. Then you do variations when n is this, when n is that. You give it, you get a general pattern. Then you use the principle of superposition to what get your final answer. Okay, so thank you very much and all the best in your exams.